So for this learning module, we'll be looking at the concept of expressing quantities in engineering notation. Before we do that, we'll review the concept of metric prefixes. The big idea of what's going on here is that since we're working across a large variety of scales in our applications, think back to learning module 1, the idea of maybe working on a nanomaterial at a very small scale or a building at a very large scale. One single system of units won't be sufficient for our needs. We will need to scale them. And the way that we will do that is by using scientific notation or adjusting the size of the unit by an order of magnitude and abbreviating it through these metric prefixes. So particularly in the SI system, if I have a unit that is either too big or too small, I can adjust its size by scaling it by a multiple of 10. And each of these multiples of 10s, as we see in the table here, has a corresponding prefix that we pronounce, and it has an abbreviated symbol that we can use to show someone what this adjusted unit is. One thing you may notice when you look at this table is that we only have exponential forms where the exponents are multiples of 3. 3, 6, 9, minus 3, minus 6, minus 9. You know that additional prefixes exist. Maybe one you remember easily is the idea of a centimeter, or a centi, I should say, 10 to the minus 2. And that is true. So why are we only reporting kind of the multiples of 3 in this case? Well, as engineers, as we'll discuss in more detail in the next slide, our instruments often limit the amount of precision that we can measure a quantity to. So in your book, they say that kind of a good way to deal with this is through expressing these numbers in engineering notation. And in engineering notation, the coefficient, that's what I'll call it, which is the number that's multiplied by this order of magnitude or this scaled factor, is always between 1 and 1,000, including 1, not including 1,000. We'll formally define it on the next page. But if we always use prefixes, which are multiples of 3, we can always have our coefficients be in that range. So other helpful hints to remember when you're expressing your units, this table is taken from the book. When you have multiple of a quantity of a unit, like 5 kilograms, as they're showing here, even though there are multiple, you only write kg, you don't make it plural. Another thing is that we can often create these compound units by multiplying or dividing. So things like a meter second, that's how you would read M times S. We'll put the dot between just to make kind of the notation clear. You can do the same thing with ratios, right? The more familiar meters per second for maybe the SI unit of velocity. In general, if you're confused whether something should be written in upper or lowercase, the majority of the time, the units along with the prefixes are written in lowercase with these exceptions that we've noted here, the Newton and Pascal SI units of force and pressure, along with some of the prefixes, mega, giga, and oftentimes these are in uppercase because the lowercase is already used for something else, like mega 10 to the positive 6. The lowercase m is used for milli, or 10 to the minus 3rd. So one thing to note is that you can actually have exponential powers applied to units. This is not surprising to anyone. If you think about a centimeter times a centimeter, rather than writing it that way, you can write it as centimeters squared. And we all recall this would just be a very basic expression for measuring the area of a surface. Compound prefixes should not be used. That's what the book says. What they mean by that is don't use multiple prefixes together. Don't write like a kilogram. You would just write, remember each K prefix corresponds to an exponential power of 10 to the 3rd. So 10 to the 3rd times 10 to the 3rd would be 10 to the 6th. Just say mega. That's what they're trying to say. That last point that I've added at the bottom is they talk about dimensional homogeneity in the book. That's just a fancy way to say that when you pick a unit system, stick with it. And when you have an equation, naturally, the units that are used on one side of the equation are going to determine the units on the other side of the equation. So you'll have an example to look at that in your homework this week. So let's talk about significant figures in engineering notation and how they go together. So we said on the last slide, when you have a number in engineering notation, it's going to be a coefficient between and including 1 and less than 1,000, multiplied by a power of 10, where the exponent is a multiple of 3. And as is alluded to in the book, one of the big advantages of writing a number in engineering notation is that it removes ambiguity in the amount of significant figures that someone is presenting. So in order to really understand that statement, we need to refresh ourselves as to what significant figures are. So it's not a learning objective for this class to kind of cover what a significant figure is. So I'm just going to kind of keep it on a high and applied level. Recall that when, as engineers, when we exchange information in the form of written numbers, there's an implication when we write the number that each of the digits we're presenting is meaningful, right? So a significant figure from like a utility point of view is just a digit that's written that provides reliable information. So in the science and engineering applications, that's going to be related to the underlying precision of the instrument. So I just so happen, this is by chance, to have my tape measure next to me. If I were to report to you, maybe you were going to 3D print a case for this phone, and I measured it out, and I said, this is exactly 6.020400 inches. Well, you might say to me, hey, I know you have a standard kind of empirical system of a ruler there, and it's in resolutions of 1/64th of an inch. I don't think those last few numbers you told me are actually meaningful because you would be limited by the precision of your instrument. And that's correct. So that's why we have to be careful when we are presenting numbers in terms of the number of actual digits we present, because there's some implied meaning in what we say. So when you think about what I mean by engineering notation, being able to remove the ambiguity, think about the number 2,400. If someone were to show that to you and ask you how many significant figures there were, what would you say? And don't think back to the actual formal rules of doing this. Maybe you have like the 8 steps or something. Just think about when you see that number. If someone's talking about, oh, that's that object has a mass of has a weight rather of 2,400 pounds. You might ask yourself, did they round that, or is the scale they're using, can it actually report out to the ones place of pounds? It could be either way. So it could be that just 2 of those digits are significant. Maybe someone's rounded. Or maybe their instrument actually has the precision to measure to a single pound, so all 4 are significant. And if we convert that to engineering notation, we can resolve the ambiguity. If only 2 are significant, we'd write it as 2.4 times 10 to the third. If 3 are significant, we'd write it as 2.40 times 10 to the third, and so on and so forth. So in our class, when we present results, particularly when you enter them into the Pearson software for your homework, we're generally going to use 3 significant figures or sig figs unless told elsewise. One thing to keep in mind as you're making multi-stage calculations, kind of allow your calculator to do the work of storing the number to the maximum precision for all of your intermediate calculations before you actually report your final value. And what I mean by that is if you're doing a long computation, don't kind of take liberty on yourself to say, okay, at this step, this is the number and I'll round it, and then keep working with that rounded number. Any type of computer, whether it's your phone, calculator, or an application within a computer like MATLAB or something like that, it's going to store the numbers that you're representing in your calculation to a very high precision value, depending upon the way that it manages its memory. I don't want to get into that now, but maybe some of you have some familiarity with programming and you're familiar with something like a double data type taking up a certain amount of bits. Long story short, the computer is keeping a very accurate representation of the number within the individual steps of the calculation. And maybe that representation actually even exceeds the number of significant figures that are meaningful in your application. But just let it do the work. Don't round anything in the intermediate. Get the final answer, and then you round according to your significant figure rules, which generally for us will be 3. So let's look at an example problem of how to do another dimensional analysis conversion and kind of look at some of those kind of steps for working with the metric prefixes. So we were asked to convert 52 slug per cubic feet to corresponding SI units. And just like last time, I gave you all of the kind of answers written out on this slide. So I will start, and I'm just going to make some notes for myself on my .cam, particularly with these conversion factors. I don't keep those memorized, particularly a slug. To be honest with you, I haven't taught a statics course in about 10 years. So I kind of have forgotten what a weird name it is for the unit of mass in the empirical system. So how do we go about solving this problem? Well, it's kind of similar to the one that we did in the prior learning module, in the sense that we basically have to just do some dimensional analysis to get the quantity that we're given, 52 slugs. Remember, slugs is the U.S. customary unit of mass, and feet, which is the U.S. customary unit of length, to SI units. So I'm just going to write here what the corresponding SI units are for mass and length. And of course, we all remember that those are kilograms and meters. So in terms of a solution here, step one, what we need to do is identify the target units. And what I mean by that is, in the last problem, they told us what units to convert to. Here, they're just telling us, hey, convert it to the appropriate SI units. So you have to be able to recognize that the quantity you're given is a quantity that measures mass per cubic foot, and identify what the corresponding SI units are for both mass, kilograms, and length, which is meters. So we'll say, just based upon the analysis that we did, that we want this as expressed as a quantity in kilograms per meters cubed. So step two, you want to identify your conversion factors. These are generally things that you're going to have to look up to form those dimensional analysis ratios. And for this problem, I've already written those down from the PowerPoint slide. You can get them from your textbook or from the table that I included in the PowerPoint slide earlier. So let's go to step three. Let's actually do the conversion. And this is all about just setting up your dimensional analysis conversion factors in such a way that you go from the units you're given to the units you want. So this is what we're starting with, 52 slugs per 1 cubic feet. So first and foremost, we want to get rid of this US customary unit of mass, which is the slug. So we want a conversion between slugs, and we want to get rid of the slug, to kilograms. So what I need to do, so you notice that this will remove the unit of slug and give me units of kilograms in the numerator, which is what I want. So we'll notice by our conversion factor that there are 14.59 kilograms per 1 slug. So effectively what we're going to be doing is multiplying by 14.59. For our last step, we need to convert from the units of length from feet to meters. So I'm going to need a foot up here and a meters, and I'll deal with that cube in a second here. But notice that in terms of the base units of feet and meters, that 1 foot is 0.3048 meters. It's kind of hard to read there, sorry. Now notice that if I leave this as is, it won't actually do any cancellation, right? Because I need to cancel out feet cubed, not just feet. So what I can do is take that conversion factor and I can just cube that as well. So if I wanted to rewrite my entire chain, I could write that there's 52 slugs per 1 cubic foot, and that there's 14.59 kilograms for each slug. And I'm going to go to the calculator here and actually do the computation. I think I have MATLAB open. That's good. Good. Yeah, you can see I was kind of playing around with this problem a little bit beforehand. If I take 0.3048 and cube it, and I let MATLAB worry about that, I go to the precision that MATLAB is reporting. When I cube 0.3048, and you don't have to use MATLAB here. If you're curious about using it and people want more coverage in the course, I'm happy to do a little bit of extra content on it. But what this will give me is the conversion factor between meters cubed and feet cubed. So I'll go back to the .cam in a minute, and you'll actually see what I'm doing there. But that number, this 0.0283, is what I get from cubing 0.3048. So that gives me a conversion factor in terms of 1 feet cubed, 1 cubic foot per 0.0283 meters or cubic meters. Now the cubic feet will cancel, the slugs will cancel, and I will get an answer in units of kilograms per meters cubed. And it's just going to be a matter of taking 52, multiplying by 14.59, and dividing by 0.0283. So let's do that. Now, in terms of what I mean by allowing your calculator to do the work, so I'm going to type in the numerator quantity that I need to multiply, 52 times 14.59. And rather than divide by actually typing in 0.0283, in MATLAB, your computational answer is always stored in a variable called answer. So I'll just type in answer here. And that's going to allow me to use the entire precision that's being stored within my calculator. So when I do that, I get the result 2.6793 times 10 to the fourth kilograms per meter cubed. Now we're going to go back and look at this here in a minute. So we're going to assume that in this case that the textbook wanted us to write the answer in engineering notation. Remember, in engineering notation, this number, the coefficient, needs to be between 1 and 1,000, so that's good, it is. And this needs to be a multiple of, this needs to be 10 raised to a multiple of 3. So 4 clearly is not a multiple of 3, but 4 is fairly close to a multiple of 3. It's fairly close to 3. So I'll just show you how to do it, and then you'll kind of see the process of why I did it this way in a minute. What I want to do is rewrite the order of magnitude that I have, 10 to the fourth, as a product of two orders of magnitude. One, which is valid for engineering notation, 10 to the third, and the other being whatever I need in order to get back to my original result. So 10 to the fourth is close to 10 to the third. So I can rewrite 10 to the fourth as 10 to the third times 10 to the first. Because when I multiply two exponential terms with like bases, the powers add. Now that will still be in kilograms per meter cubed. Now I can absorb this factor of 10 to the first, into the coefficient, 26.793. And that's good because that's still between 1 and 1,000 times 10 to the third kilograms per meter cubed. Now you might say to yourself, in engineering notation, we would typically want to take that and replace it by a prefix kilo. But why wouldn't I want to replace it by a prefix kilo here directly? Well, notice that I already have one here. And in the book, they brought up the idea of don't stack or chain these prefixes. And what they mean by that is don't use a prefix 26.793 kilograms per cubic meter. What you want to do is take and combine those two prefixes together. Remember that kilo is 10 to the third. We know that. And if you have two factors of 10 to the third, this would just be 10 to the sixth, which is mega. So that's how on the slides I'm getting that answer of 26.793 megagrams per meter cubed. Now, you might ask yourself, well, he didn't round to 3 sig figs here, and that's correct. So let me do that. This would be 26.8 megagrams per meter cubed. So hopefully that emphasizes some important points to you, namely the idea of not stacking prefixes, along with the fact that you can, if you need to relate kind of squared or cubic units to one another, you can take the conversion ratios and just square or cube them as needed. So hope that helped, and we're done with chapter 1, believe it or not.